Next up in level 2 chemistry is 91165, demonstrate understandings of the property of selected organic compounds. So organic carbon-based chemistry. So I'm going to be using the formula sheet which is given and the most common calculator, the Casio FX, to solve these. Okay, so with that said, let's do it to it. So a lot of organic chemistry is nomenclature, that is knowing what something is called, either the common name or the IUPAC name. And this is a fairly standard organic chemistry chart. They give you the name here and they want you to draw the rough structure, or give you the structure and they want the name of that. So let's go through how we would solve these. First one up is ethanamine. Let's look at ethanamine. So the first thing I'm going to see here is there is an F there, which means that there are going to be 2 carbons in a chain. There may be more carbons, but probably not, given the name of this. And the second thing here is there is an amine. So what does that mean? If we have an amine, we're going to have the carbon with 2 hydrogen on it. So really what we want is carbon, and when I'm not going to draw them in this shape here, I'm just going to draw them like they draw them here just in a straight line. So we've got our 2 carbon there, and then we need to, on one of those carbons, and it doesn't really matter which end it's going to be. So let's do the hydrogen, and now we fill in the rest of these hydrogens. So remember, carbon has 4 bonds to it. So 1, 2, 3, 4. This one has 1 already, so it needs 3 more. We're going to presume that the hydrogens are all going to come along for the party, no problem. And that's that. That's how we would draw that. Next one. So let's look at what we've got. So we've got here 2 bromines. So it's going to be dibromo something. And there is 1 carbon, so it's going to be, meth is going to be in there somewhere. So is it a methane, methine? It's just a regular carbon by itself, so it's going to be methane. So the whole way through this, that's all we need to say. So it's going to be dibromo, so a halokane here, and dibromomethane. I mean, that's pretty much going to be what it is. All right, next one. So the next one is 3,3-dimethylbutanoic acid. Bit of a mouthful. So there's a lot of stuff going on in here. So the first thing we're going to look for is our sort of meth, eth, bute, prop, that kind of stuff. There is a meth there, and there is a bute in there. So this says to me there's going to be some branching off. So what is the longest one? Oh, it's the bute here. So there's going to be 4 carbons in a row. That's going to be taken as a given. Now, how do we work out what else is going to happen here? So there is butanoic acid. So what does that mean for us? So the noic acid is always going to have the form O double bond, carbon, and then this kind of hydroxide thing, almost like an alcohol. So let's do it to one end. Let's do this here, and we can have the H however we want, but I'm going to put it like all of the atoms there. So this carbon is at Associated with bonds, there's 1, 2, 3, 4, so that's all it can take. The oxygen here, it's got all the bonds that it can take. Remember, oxygen is 2 up from carbon in the periodic table. Now we get to the dimethyl. So if we had methyl, it would just be just carbon by itself. In fact, there are 3 of them here. So this is the functional change here. So I'm going right to left. So this is 1, 2, 3, 4. So on this one here, there's going to be a carbon and a carbon. So this is what the 3, 3 means. And now we just add the hydrogen. So this one has 1 bond already, so it needs 3 more bonds, and the hydrogen's going to give that to us. This carbon here has 1, so it's going to have 3 bonds by itself. I'm getting a bit cramped for room, and this one is going to be the same here. So double check, have we got everything? On the third one, do we have 2? Remember, the di means 2. Do we have 2 methyls? Yep, we've got that. Do we have butanoic acid? Well, we've got 4 in a row here, and on the first one, we've got this kind of chain that we need to have. This one here, that's there. There's nothing else there, so it's a bit of a mouthful to say it, and it's a bit of a complicated molecule. They don't really give you a lot of space, but that's what it would be. Next one, so there's this kind of beastly looking molecule here. Let's break down what we've got. First thing we're going to do is we're going to look at the longest chain of carbon, and there's 1, 2, 3, 4, 5, 6 of them. It's not a single bond, there's a double bond here, but there's still 6 in a row, so it's going to be hex something. So it's going to be hexane, hexene, hexine. It's going to be hexene there at some stage because of this double bond. All right, what have we got that's complicating things? Well, we've got this bromide here, this bromine. So how is this going to change things around? It's going to be interesting, isn't it? So this is going to be, the ene is going to be where we start from. So this is going to be the first, second, third, fourth one, and it's going to be there. 2, 3, 1, 2, 3, 4, 5, 6. Yeah, we're going to go from right to left because that's the functional part there. So it's going to be bromo something, and it's on the 4th. So this is going to be 4 bromo something, and there's going to be hexene there. Next is, we want to know where this hexene is, isn't it? So the thing which is fouling things up for us is this 2. So it's not going to be hexene necessarily. It's going to be hex 2-ene. And there's only 1 bromo. So I think that's it. So it's going to be 4 bromo. And then we have to say that there are 6 on this longest chain. And on the second carbon is the ene, the double bond. Is there anything else which is complicating things? No, there's nothing else that's attached there, so I think that's what it is. 4 bromo hex 2-ene. A lot of information in that word there. It's a bit of a strange looking molecule. I'm not quite sure what that would be used for, but anyway. Next one, 1-pentine. You remember the first thing we're going to look for is how many carbons are on the longest chain, and there's 5 there. So let's link them up. 1, 2, 3, 4, 5. Is there a halogen or anything attached to it? No, it would tell us. Next thing we're going to look for is the tine, and if there is a tine, it just means that one of these bonds is going to be a triple bond. And where is that triple bond? That triple bond is on the first carbon, so that tells us that this carbon here is going to be double bonded. Are we done? Well, no, we need to saturate these carbons. They need to have their hydrogens attached. So let's attach a hydrogen there, and this carbon's got 4 bonds. This carbon here now has 4 bonds. That's nice and happy. 1, 2, 3, 4. This one here only has 2, so it needs 2 hydrogen. This one only has 2 bonds, so it wants 2 more hydrogen. This one only has 1 bond, so it needs 3 hydrogen. Alright, the next one here. Let's have a look. There's a fair bit going on here. So, the longest carbon chain I can see, well, there's 2 chains of 3. 1, 2, 3. Well, 4, I guess. 1, 2, 3. 1, 2, 3. 1, 2, 3. So it's going to be... prop is going to be in there somewhere. Okay, so what are the bits that are here? There is a methyl here. So there's going to be methyl in there somewhere. There is a hydroxide branch here, so it's going to be an alcohol, so it's going to be something ol. There's more than one functional group here, so let's number them. First thing we're going to do is this methyl, which is on the, it doesn't really matter which side it comes from, say 1, 2, 3. It's going to be the middle one, so this is going to be 2 methyl, and then we have to say that there are 3 carbon. They're all single carbons, so it's going to be propane. Because it has an alcohol, it's going to be an alcohol on the second carbon in that chain. So this is 2-methyl propane 2-ol. So this question, or some variant of it, is in every year's exam. It really does behoove you to really know what these functional groups are, what the halogen functional groups are, what the difference between an ane and an ene and an ine are, etc. In the next question, we are given a sort of rundown of an experiment. And in physics and chemistry exams, they always give you one of these classic experiments, and this is one of those classic experiments. So explain how acidified dichrominate solution, which is Cr2O7 -2 ion with hydrogen ion, can be used to distinguish between compounds G and H. It's normally actually a potassium chromate, so potassium dichromate, but they seem to miss this out. Maybe not to get too hung up on it. Okay, this is a classic experiment that you would have done in class. So when we do that, we're going to say, we've got 2 pots here, so this is G, and this is H. And we put some of this in to both of them separately. What is going to happen? Well, what's going to happen with G is nothing much anyway. It's going to stay the same color and you're not going to be able to notice it. So the type of reaction that we're doing here is a classic reaction, which is oxidation to find alcohol. And we can even use it to have primary alcohol, secondary or tertiary. So what's going to happen is this thing is going to be kind of an orangey color. When we put in the alcohol into that, mix it with alcohol, it's going to turn green. It's a really quite clear distinction between something and nothing. If it turns green, it's either primary, secondary, or tertiary. We can never work out using the shade what type of alcohol it is. So here's a picture of one. So as you can see, it's pretty easy to see which one is which. So include the conditions required to do this. It's an oxidation. You probably require heat because it's an endothermic reaction. It's such a strong reaction, it's turned my pen green by the looks of it. So it needs to be heated. So it will require heat at least to get going. Okay, what else are they? Describe relevant observations. So the observation, you might see a bit of bubbling. You'd have to distill it. So you'd have to distill it first. Otherwise, it probably won't work properly. The main thing you'll notice is the color. All right. Now, they say draw the product form. Where is it going to end up? It's going to end up as some form of carboxylic acid. But it's not going to go there directly. It's going to have partial oxidation first. And maybe we should go through there what's going to happen. So we start off with the C5H. How many H's? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And one oxygen. So we start with this sort of classic alcohol makeup here. Carbon, 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 and then the methyl bit is here. So these all need their hydrogen. Come on. So each of these carbons has to have 4 bonds. 1, 2, 3. It needs hydrogen to be whole. This needs 3 hydrogens to be whole. This needs 2 hydrogen. And this has got 1, 2, 3, so it needs another hydrogen. So that's what we would start with. It's 3, what would it be? 3 methyl butane 1-ol, I guess, because the alcohol is on the first carbon there. And then it's going to undergo partial oxidation. So it's going to lose 2 of those hydrogen atoms. And to make up for that, the oxygen is going to become a double bond. So it's going to become something else. It's going to become an aldehyde. So in this case, let's see what's going to happen. So the oxygen is going to have 2 bonds now. And the carbons are going to be, those 4 carbons are going to be there. And then this one isn't going anywhere. Let's do the hydrogens this way. 1, 2, 3 hydrogens, 4 hydrogens. This one has 2 bonds, so it needs 2 hydrogens. This one has 3 bonds, so it needs 1 more hydrogen. So it's going to become an aldehyde. So it's going to have, what's it going to be? It's going to be C5H10 now with an oxygen. And then the last step is it's going to become a carboxylic acid. They all do. So last thing, it's going to become some kind of carboxylic acid. I can never spell it right. Some type of carboxylic acid. And it's going to pick up an oxygen. So these chemicals are going to mix up, and we're going to have, what are we going to have? C5H10O2 now. And let's have that oxygen. Double bond is going to be there, but now it's going to pick up an oxygen, and this oxygen is going to need hydrogen, and then otherwise it's going to look exactly the same. This needs 3 hydrogen, this needs 1 hydrogen, this needs 3 more hydrogen, this needs 2 more hydrogen. This has already got enough bonds, this only needs 2, and this is done. And what is this going to be? This is going to be, what is that? 3. So 3 methyl butanoic acid, because it's got as the functional group there is this whole thing now. So, and there are 4 of them. So but acid. I don't think there's anything there. Yeah, so it's going to get there through reflux and distillation. So we're going to heat this up, stir it around. It's an endothermic reaction, so it needs that heat to distill, and then it's going to partially oxidize and become a sort of intermediate step in aldehyde, and then it's going to pick up that extra oxygen to become carboxylic acid, in this case 3-methyl butanoic acid. If I got that wrong, no doubt someone in the comments will tell me. Next question, we're told that haloalkanes are useful starting materials used in the synthesis of more complex molecules, including many pharmaceutical products. True. Below are some constitutional structural isomers of chloropentane, C5H11Cl. Use these to answer parts 1, 2, 3. So the first one is classify each of these haloalkanes by either primary, secondary, or tertiary. Now the haloalkane, the thing that makes the haloalkane is this, where can I put it? Is this CCl bond here. So that one there, this one here, this one here, and this one here. So a primary is when this carbon is linked to one other carbon. A secondary is when it's 2 other carbons, and a tertiary is when it's linked to 3 other carbons. So this one here, G, the carbon is only linked to this one here, 1. So G is a primary haloalkane. I, so this is the carbon that we're looking for. It's attached to 1, 2, 3 other carbons. 1, 2, 3. The Cl is, of course, chlorine. So this is a tertiary. J, J is this one. So this carbon is attached to one other. So this is primary again. And K is attached to 1, 2, 1, 2. So this is a secondary. So here's one. This doesn't count. It's the chlorine. And this is the other one. So it's secondary. Next, we're told that compound K forms 2 different products when reacted with alcoholic potassium hydroxide, KOH, and heat. So it doesn't give us the end of this equation. So draw both products of the reaction and circle the correct label. Okay, so this thing with a halogen in it, it's going to, an alcohol, it's going to lose that, and it's also going to lose one of those beta hydrogen. Okay, So we're going to get some C5H3, 4, 5, 6, 7, 8, 9, 10, 11, 10 isomers of that. Okay. Plus, guess it's going to be potassium chloride. And it picks off one of those hydrogens, so it's going to be water. Okay, so the two ones it's going to use here, it's going to be C, 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 C. Let's put those in first. It's lost one of those. It's lost one of those hydrogens from the end, so it's going to be that one. So that's going to be our minor because it's the first one substitution, and then the other substitution is this double is going to be in the middle. This is nice. Yeah, it's going to be in the middle there. So this is going to be minor, and this is going to be major. So this has got two bonds, so this needs two hydrogen. This has got three, so it's got one hydrogen. It's got three, so it's got one hydrogen. And this needs three hydrogen and three hydrogen. 3, 6, 7, 8, 9, 10. Yep. And this one's going to have three hydrogen, one hydrogen. This has already got enough bonds. It's going to have three hydrogen. This is going to have three hydrogen. 3, 6, 7, 8, 9, 10. Yep. So the equations balance up, but this is going to be our minor. This is going to be our major. So why is one the major and why is one the minor? The minor one. Then the reason why one is the major and one is the minor is that this one has to over has more. It's kind of a byproduct of, well, not byproduct. The minor one is kind of an intermediate product for this one, and this is going to be the more stable, and this is the one that has the most substitutions. So we can justify it by I can never spell this guy's name. Is it Zaitsev or Zaitsev? I can never remember this guy's name, but it says that he says that the major product is always the more substituted one, a compound. So it's the one that it tends towards an equilibrium. Maybe equilibrium is maybe a bad word, but it's the one that's going to require the most beta carbon or beta hydrogen transformations. So let's do the major one here. The major one is going to be, what did we do up here? Carbon, carbon, double carbon, carbon, H, 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 needs one more H. 1, 2, 3, 4. 1, 2, 3. So this needs an H. And this needs 3 H's. What's that going to be called? Oh, I got that wrong. So this one is going to be there because it has this methyl thing, isn't it? Doesn't it? And that's going to have 3 8. So what's that going to be called? That's going to be on the third on the second one. So this is going to be 2 methyl. That's on the second one. 2-ene. So 2 methyl 2 butene or 2 methyl but 2-ene. And the minor one is going to be this one here, which is carbon, then double, single, carbon, single, carbon. There's one bond, so we need hydrogen, hydrogen. This one has 1, 2, 3 bonds, so it needs a hydrogen. This needs 3 hydrogens. 1, 2, 3. This needs 1 hydrogen. Again, I'm not doing, Vesper theory. I'm just showing where they are. And this one has 2 bonds, so it needs 2 hydrogens. And that's our minor. What's that going to be? It's going to be same as this, except this double is moved to the side. So this is going to be, and this thing here, this methyl is going to be on the 3rd carbon. Now, if we start from functional group here, so this is going to be 3 methyl butene, because it's between the first and the second, so the second ene, but they don't ask for the name anyway, so that's what that would be called. To get the full marks, you'd need to say Zaitsev or Zaitshev's law, the major product. Maybe I should add a little bit more here. Why is one the major product and one is the minor product? And it is this kind of poor gets poorer a way of saying Zaitsev's rule. This carbon here is the carbons that they're attached to these other carbons are more numerous, whereas this carbon here is only attached to one other carbon. These carbons are attached to one each, so there's 2 of those. In fact, this one is attached to 2 carbons. So the fact that these are attached to more carbons than this one, so this is attached to 0 and this is attached to 1, this one is attached to 1 and this one is attached to 2, makes this the major product, because this is the more stable product. It's going to take a lot more energy to break that one up, I guess you could say. So we're on to question 2. An incomplete reaction scheme is shown below. So it's a chemical algorithm, what I like to call them. Draw the structural formula of compounds B, C, and D. So where's B? B is here, C and D, and then we get E there. Complete the reaction type W, X, Y, and Z. Okay. And complete reagent 4, which is here. Okay. This is pretty similar reaction to what we had last time. You notice the potassium. So what's going to happen here? So there's 2 reactions just breaking off here. This is going to be, what is this going to be? This is going to be a substitution reaction. A compound, this is going to do. Ooh, what is this going to do? So it's going to, the bromine, what's going to happen here? So this is going to be nucleophilic substitution. The bromide's going to go. Where the bromide goes, what are we left with? Because something else has to happen here. So we're going to attach this to the alcoholic ammonia. What's going to happen with this potassium hydroxide? Ooh, let me have a think. What's going to happen is that the potassium is going to replace the bromine, isn't it? This nucleophilic substitution. So we're going to replace that with an OH, aren't we? Yes, we are. So we're going to get C, 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 and they haven't given us enough room. C, 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 C. And this other C is up here. And this one here now is going to be OH. Yes. That was going to be OH. Now we have to work out the hydrogens. So it's hydrogen, hydrogen, hydrogen. This has got 1, 2, 3 bonds, hydrogen. 1, 2, 3. This needs a hydrogen. This needs 3 hydrogen. This needs 2 hydrogen. And this needs 3 hydrogen. What is that going to be called? That's going to be, there's our alcohol here. And then we've got a methyl group here. So this is going to be 1, 2, 3 methyl pent 1, 2, 3, 5 pentane. Alcohol is on the second. 2 ol. Oh my god. Alright, and this one here. So the Z one here. So the bromide is going to get taken off. This is going to be the same, isn't it? It's going to be nucleophilic substitution. Nucleo. I can substitution, and so this is NH3. What is this one going to be? This one here, the bromine is going to be substituted for amino, isn't it? It's going to be an amino. Yeah, it is going to be an amino. It's going to have the NH2 in there somewhere. Where is that going to go? It's on this. It's on this one here. And they're all going to be singles, yes. So we've got 1, 2, 3, 4, 5. This one here is still going to have that methyl group. And this one here is now going to have, not an alcohol, it's going to have the NH2, isn't it? Yes. Okay, let's put the hydrogens in. Hydrogen, hydrogen, hydrogen. I'm not checking to see that these are properly balanced. So this needs a hydrogen. This needs 3 hydrogens. This needs 2 hydrogens. This needs 3 hydrogens. So what is this going to be called? I actually have no idea what that's going to be called. Oh, we'll just check. One moment. Now that we've done that, what we've got here is this. So it's going to create 2 products. I guess this is a kind of a heads up for us. And concentrated sulfuric acid. What is this one going to be? This is going to be elimination by dehydration, isn't it? So that's going to make an alkene. What alkene is this going to give us? Good question. Let's count the carbons. So 5 carbons. So there's carbon, carbon. Gee, they don't give us much room, do they? Carbon, carbon. And then there is this sort of rogue carbon there, which is the same as this one here. So if I'm muttering, I'm just kind of, and we're gonna need a double bond here, aren't we, to make it an alkene? Yes. And which one is going to be minor and which one's going to be major? This one is going to be the major. Okay, let's is there anything else there? No, the bromine's gone. So I'm not going to add the hydrogen. I'm just going to do it the way that they do it. H2 H, that's full. H2, H3. Otherwise, this is going to be a mess. All right, now we've got that. So we don't worry about this. This is our minor. This is going to be our major. This is what we're going to be left with anyway. Now, there's chlorine in here. So we are going to add something with chlorine. And it's going to be hydrochloric acid, isn't it? This chlorine has to come from somewhere. So it's going to be concentrated hydrochloric acid. Make it real strong so it does the job. And that reaction type, well, we don't even need to worry about working out the atoms of the hydrogens. What type of reaction is that going to be? That's going to be addition. Well, we're adding hydrogen, so it's going to be electrophilic. I can never spell it. Was a 1L or 2Ls. And that's that, I hope. On to B. So compound E shown here can be redrawn as below to enable it to be viewed as a monomer suitable for undergoing additional polymerization. So polymerization is essentially where we cut and paste this monomer over and over and over again, making sure that we have the bonds ready. So draw the 3 repeating units of the polymer that will be produced using this monomer in the box below. So what's going to happen is that this double is going to become a single. Let's rewrite this, and I'm just going to not worry about the that monomer. Yeah, I'm not going to draw all of those atoms, but that's there. And then this is going to just repeat, isn't it? So it's going to be end to end. CH2. Then it's going to be this complicated one again. So it's not going to kind of go, let's see, H, and we could kind of go dot, dot, dot. And here we're going to have this here and then end that with the C4 H9 business hydrogen dot dot dot. So it's the same thing. So we would draw this like that if you wanted to, although I don't think that would get you the marks, and you'd have to make note double bond would go. Okay. So then we're asked to basically explain what happens in this polymer. So in your answer, identify the structure and bonding feature of compound E that makes it suitable to undergo additional polymerization. Well, it's unsaturated. It's got hydrogens that it can play with. And what's going to happen is that what sort of bonds are we going to have? The pi bonds are going to make way for sigma bonds. So in other words, this double is going to make way for a single bond, and that's going to allow us to repeat. It's iambic, if you want to be Shakespearean. Explain on, off, on, off, on, off. So explain how an additional polymerization reaction occurs. Well, I can see here this pi bond will break and will be replaced with a new covalent sigma bond. So if you can't read that, compare the relative reactivity of the monomer and the polymer. So the monomer must be more reactive than the polymer. Otherwise, it wouldn't happen. It's always going to go from more reactive to less reactive. And what's causing that is what is going to be causing that? So we go from this kind of this bit up here where it's electron rich to more electron efficient, let's say. I won't say electron poor, but in this sort of beast here, the electron's doing a lot more work. And it's going to be relatively inert because of that. So, yes, those double bonds are going to give way to single bonds and carbon-hydrogen bonds. I think that's how you would answer that. Right, so now they tell us that polytetrafluoroethylene, better known as Teflon, is a polymer known for its use in breathable, waterproof textile fabrics and cooking pans. Alternatives are being developed that aim to provide similar advantageous properties to Teflon with less environmental impact. The structure of Teflon is shown below. In the box below, draw the monomer that Teflon is made from. Well, it's already a polymer, so the monomer is going to be CC, F, 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 and then the secret sauce here is going to be that. It's going to have a double, and when it's polymerized, it's going to lose that and become a single bond. Okay, Teflon is used in non-stick cooking and non-stick coating on cooking pots and frying pans. Identify the physical and chemical properties of Teflon that make it suitable for this use. Well, it has a very, very low frictional coefficient. I can't remember what letter that is, but it makes it really sort of slidey. You can slide things along. An interesting use actually is that in Chernobyl, the large container thing that they built, a huge structure that went over the top of it, wasn't on rails. It was on a really long Teflon strip, and they made it really easy once they built it to sort of slide it over the sarcophagus of the Chernobyl nuclear power plant. What else does it have? It has a high melting point. Okay, if you're making your pots and pans out of Teflon, you don't want them to melt. It's also not going to warp. Now, it will eventually, but at a really, really high temperature. The chemical property, it's inert. It has these carbon fluoride bonds, which are really, really strong. What else? It's almost like a surfactant, and that I think it's hydrophobic. I think, and that the oils and the any other alkali that you can put on it are not going to break away those bonds. So you're not going to be eating your steak and have bits of fluoride in it, which is quite a good thing. The next one says that we are to draw the 3 straight chain non-branched isomers of C5H11 chlorine. Okay, so this might be intimidating, but think about it. So if this is straight chain, that means that all of these carbons are going to be in a line. So it's going to be carbon, 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 carbon. Now, this is going to be pentane something, something pentane, something pentane. We're adding chlorine into it to make a chloride solution. Remember, I think it's chlorine by itself. It's chloride when it's in something, and it's a halocane, so it's going to be chloropentane, 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 and then it's going to be where do we put this chloride? What's going to be 1 chloropentane, 2 chloropentane, 3 chloropentane. So here we're going to put the chloride there, and here we're going to put the chloride here, and here we're going to put the chloride here. It doesn't make any sense to put it here because then we're just going to get back to here. Because remember, this is the functional group, so this is what decides our numbering. So if we put the chloride here, it's just going to be exactly the same as that, only sort of stereoisomer. So now that we've done that, we need to measure things off. So this is going to have hydrogen, hydrogen, hydrogen. It's going to have hydrogen, 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 and it's got 1, 2, hydrogen, hydrogen. Let's make sure that we've got it. So we've got C5, 1, 2, 3, 4, 5. Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of these hydrogen and 1 chloride. Cool. All right, so we can just repeat. I guess you don't need to really draw these H's in there. Yeah, 1, 2, 3. Going exactly the same as that. Then hydrogen, hydrogen, hydrogen. Making sure we get the single bonds. And we do exactly the same thing here. So it's going to have double. 1, 2, 3. It's going to have hydrogen, 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 hydrogen. Make sure we absolutely saturate that sucker. Single bond, single bond. That's what it's going to look like. Looks intimidating, but not really. Now we get to question 3. So Pahitakawa bark can be brewed into a tea and used in a range of rongoa, which is traditional medicines. Full stop, no capital letter. As it contains the organic acids such as ellagic and gallic acids, probably mispronounced that, which have antioxidant, antiseptic, and anti-nausea properties. Good for us, the rongoa. That's how you pronounce it. Rongoa. Because it's got the macron over the A. Yeah. While extracting the Pahitakawa bark, following compounds can be isolated. It's the gallic acid, 1 heptamine, 1 propionamine. Okay, name the functional group. What's the carboxylic acid group? I can never spell acidic acid group. Spelling. Okay, explain the procedure you could use to distinguish the heptanamine and the 1-propionamine solutions based solely on their physical properties. Physical properties, limited difference, melting point, boiling point, water solubility. You'd probably go water solubility for this one. So you would put each into a test tube. You put the top on the test tube with water. You would shake the living out of it, and one of them is going to dissociate, one of them is not going to dissociate. The one that dissociates will be, the one that dissolves, really I should say, is going to be the proper namine, and that's going to become clear, a clear solution as it dissolves, and the other one will not dissolve, and it will probably form like a little layer at the top. There will be like this little, almost like an oil slick layer at the top. And the reason why is that it is hydrophobic. It has a great big long tail here. So it has these two hydrogens coming off it, and then it has this kind of 1, 2, 3, 4, 5, 6, 7. It has this little tail, and this is going to repel water. So it's gonna form a layer, and it's probably less dense than water, so it's probably going to float. As an aside, we could exploit some of the another physical property of these two. So this is the propylamine. I think that's the other way of saying it. Let's have a look at the boiling point. So the boiling point of this is generally accepted to be around about 48 degrees by these organizations. 48, 49 degrees at sea level, I'm presuming. And the other one, the heptanamine, this long beast here, has a boiling point of 154 to 156 by the looks of it. It's fairly accepted. What does that mean? Well, it means that we would take a vial of one or the other. We wouldn't put them over a Bunsen burner, probably. We probably would put them in a bath of water, and then we would probably heat that up over a Bunsen burner. Reason being is that if we put Bunsen burner something which has a boiling point of 48, it's just going to go whoosh, and we don't know what type of gases are going to be released. So the less complex one, the prop, is going to boil first, and then this other one is not going to boil or evaporate at all. So describe how red and blue litmus paper can be used to distinguish between the gallic acid and the that one solution. Include observations in your answer. Well, we would just take the red and the blue and test them with each. So for the gallic acid, I mean, it's acid, and presuming the litmus paper does react to it, the red litmus paper is going to stay red, and the blue litmus paper is going to go red. For the one heptanamine, the red one is going to go blue, and the blue one is going to stay blue. Okay, devise an alternative method without using litmus paper to identify the acid with the functional group with the gallic acid. Oh, okay, this is a good question. In your answer, state the reagent needed and the general products formed. Describe the observation and link to the products formed. Probably the best way to do it would be a base acid reaction. So you would use something like bicarbonate soda, sodium bicarbonate, which is, what is that going to be? NaC2O, I think, O2, could be wrong. Sodium bicarbonate are a strong base anyway. So you're going to put it in, and you're going to notice if it does have it, it's going to have effervescence, and I can never spell this one. Effervescence, it's going to bubble, and it's going to make water plus carbon dioxide. So it's going to form a salt as well. So it's probably going to what is this actually? It's a what's it going to form? It's going to form sodium hydroxide plus water plus carbon dioxide. And on to the very, very last question. Putakawa flowers contain many terpene compounds, volatile organic compounds that contribute to their fragrance. Okay, you learn something. An example of a terpene, nerol, is shown below. Two functional groups, A and B, have been circled, shown on the right, where the label R has been used in place of the complex remainder of the molecule. R1, R2, R3, R groups are all different. So for this one, we are probably going to be looking at geometric isomers, whether they're cis or trans. So we're going to presume that R1, R2, and R3 are not these, not H3C there, and that they're all different and they're not just hydrogen by themselves. Okay, which one can be a geometric isomer? Well, A cannot be. So in order for this to be able to be a geometric isomer, it has to be a stable or restricted, really restricted is a better word for it, formation. And there is this sort of this carbon double, so we can't have this thing kind of migrating over to this side or this thing migrating over to here. Okay. The other thing that it's got to have is that the orthogonal groups must be different. So here, these two are the same, and they're different from there. This one, this one, this one, and this one, because we're told R2 and R3 are different, and that they're different from these as well, otherwise there would be H and H3C. These are all different. They're locked into place along this axis, so therefore only B can exist as a geometric isomer. So B has two geometric isomer. It has a cis and it has a trans. So it will be H3C, HCC, and then R2, R3, but it can also have the R3 up here. So this would be the cis, this would be the trans. And that's the question. So all in all, reasonably challenging exam. It's certainly taking a long time to do. Probably a little bit tougher than the last chemistry exam that we did, the structure and bonding one, but a pretty good exam. No easy marks, but doable questions.